So first of all, I don't know how many people were here last year and heard me give this talk or give a previous version of this talk. Okay, a couple. All right, good. I'm glad most of you weren't here because things haven't changed and improved quite as much as I would have hoped. But that's okay. What's more important than ISOC, my ISOC connection here is I have been the chair of the NTP working group for a number of years, and I'm also the chair of the co-chair of the IEEE 15.8 Security Subcommittee. So let's just go ahead and get started. So the first thing, it probably goes without saying that accurate time needs good security. For a long time, the time community didn't really believe this. And then in the last number of years, we've seen a number of things that have proved otherwise along those lines. Performance has always been the time community's key motivator. We need precise, accurate, synchronized clocks. And, you know, time information is not secret, so why do we really care? Well, it turns out where you get your time from and if it's been modified in transit, a number of these things actually turn out to be pretty important. The corollary to that actually turns out that good security also needs accurate time. And there's a number of security protocols out there that actually depend on the fact that the clock is synchronized. And you're beginning to see solutions come out from a number of different places that actually are sort of bypassing the time synchronization protocols that are out there to sort of get that initial value of time from some sort of proven and reliable time source. So, as I've already said, security has not really been a high priority for the time synchronization community in a long time. But a number of things have specifically changed, I think, over the last few years, at least the time that I've spent looking at this area. First of all, there's a lot more interconnection and decentralization. Also, we're seeing increasing evidence of the impact of inadequate security, the interdependency between security and time, and then also it turns out legal and compliance requirements. One of the key people that's really been sort of pushing me to try and get this done has a number of legal issues that they would like to see. And the only time I've actually ever been called by somebody as a potential witness in a case had to do with time synchronization and security, which fortunately I was unable to given my job, my previous job, I was unable to actually help out in that case. Something that I was not too terribly sorry about. So first of all, as we have seen in the news many, many times, attacks are occurring. The most notable one are the various ways that NTP can be used as an amplification attack. I'm going to talk about two time synchronization protocols throughout the course of this presentation, NTP and PTP. NTP is the most widely deployed, and it's the one that you're going to see all of the security attacks on. PTP, you haven't really seen a lot of security attacks on yet, I think primarily because of where it's deployed and the scale of its deployment. But as we've seen in any number of other technologies, as that scale increases and as the people become more aware of it, then it will also become a target. Vulnerabilities are constantly being discovered. I don't know how many of you are familiar with the Network Time Foundation. They maintain the NTPD code base, and in the last year or two talking to them, they have seemed really frazzled about the number of vulnerabilities that they're getting reported to, and a fair amount of frustration about not being able to get to some of the new and interesting things that we're interested in working on because they're spending all of their time addressing vulnerabilities. So, also research is occurring. I'm definitely not an academic, but I can tell you that at a number of conferences recently, there have been papers. This one actually was from NDSS in San Diego, and this one was specifically dealing with some time issues, and there have been a number of others that have been published. I've seen some published at USNIX and a couple other conferences. This one in particular is going to be presented at the Advanced Networking Research Workshop that's going to be held in Montreal in conjunction with the IETF. So all of this research is occurring, and yet, after all of this time, and after 8+ years, we still have no new specifications for time synchronization security. And on the one hand, I find this terribly frustrating, and on the other hand, I feel a tad bit guilty because I have actually been involved in all of these activities. So, it is way past time to secure time. There are multiple sources of problems. There are flaws in operations, so things where the protocol is configured or implemented in a way that causes issues. There are weaknesses in the NTP protocol itself that can be exploited. And then finally, there's the fact that there's no adequate security mechanisms built in. So I think a lot of times, at least initially when we started looking at the security problem, we were all gung-ho to go define a security mechanism. But a good portion of the attacks and a good portion of the things that you're seeing there don't have a lot to do with whether we authenticate NTP or not. They have a lot to do with the structure of how NTP is built, the way that it's deployed, how it's configured. It was originally designed in a world where it was a just happier, friendlier place. And we didn't imagine that people would do some of the evil things they think up these days. So the existing time security specifications for NTP, we have pre-shared keys built in, but this mechanism does not scale at all. Currently, as NIST or USNO actually mails out the keys on a monthly basis to a select set of clients. The auto key specification was developed. It was immediately found to be flawed. The IETF security community was not accepting of it, and it was published as an informational RFC with the mandate that you all will go off and develop a standards track security mechanism for NTP, won't you, any day now. Then IEEE 1588 came along. Version 1 had no security at all. Version 2, we specified Annex K, which was an experimental annex, and it was published. There was some initial testing done on it, and it was proven to be flawed. And so now we're in the process of working on version 3, and it will have a new security solution. Now, we have talked about requirements, and I've often heard people say you spend a lot of time talking about requirements. You need to actually move on to the solution. But we've done a fairly detailed analysis of requirements, and this has sort of become the foundational document to at least be able to define what the requirements are that are associated with time synchronization protocols in general. So now I'm going to move on to NTP and sort of the status of the time synchronization security work there. So the IETF approach to the problem has been to look at all three of those areas that I talked about earlier. In the flaws in configuration and implementation of existing protocols, an NTP BCP was developed. Weaknesses in the protocol itself, tweaks and clarifications, we're attempting to get some of those done. We've also been sort of talking in the background about potentially doing an NTP v5. And the lack of adequate security mechanisms, well, that's the network time security, which I will get to momentarily. So the BCP. Oh, you know, I never, fascinating. Looked at the wrong thing on here. So I've actually already spoken to this slide because I was looking at it over here, but you get the idea. So the next one is to go into a little bit more detail on what these are. The first one is the BCP. It was proposed, and I went ahead and put up to give you all some sort of a sense of a timeline. On your right is from the IETF data tracker. So anytime you're interested in the history of a document, if you just go to datatracker.ietf.org, and for every document that is in process, you can find the timeline for it, and you can see where it spent more time and where it spent less time. So this one, so the BCP has had a lot of community input, and it should be published. It has been submitted for publication. It contains a lot of the same information that you will find from any number of vendors and operators out there that have published best practices associated with NTP, and in particularly addressing the amplification attack for NTP. We're also in the process of updating a MAC for NTP. This is a really, really short document, but basically it says, yeah, we agree MD5 is broken and maybe it's about time for us to replace it. And I know that that's a little bit overdue, but that's what we did there. The NTP client data minimization draft was actually brought about by privacy concerns and the linkability issue that's been brought more to the forefront in recent years. This draft is actually currently expired, but we did have some recent implementation experience with this there was a hackathon, IETF hackathon held at the African Internet Summit a few weeks ago, and one of their projects was to work on an implementation of this. So I think you're going to see a quick resurrection of this draft and a publishing of it. It's a very simple modification to NTP that just clears out some fields that aren't necessarily needed. And finally, we get to the NTS draft. And I'm really working on a positive attitude for this draft, but I'm struggling a bit. It's been quite a chore to get where we are. And we've had, we had an initial version that some researchers from Germany went through and did, and they published it, or they didn't publish it, that we put it out for working group last call. And the security community just rained all over it, asked us why we were reinventing the wheel, and we went back to square one. And then we had the second one, which we sent out for working group last call last fall. The time community came back and said, "What are you doing? Are you nuts?" And so we're now in the middle of resolving the "what are you doing? Are you nuts?" process. As part of that, one of the real challenges with NTP is you have your server client mode of service, which is a relatively there's a number of people who believe that's the mode that most people really care about. It's not the only mode that exists, though. NTP also has symmetric modes and a broadcast mode, and it turns out that those are all different models of communication, and finding a single security solution that fits them all is proving to be really difficult. So the current draft, which is draft 11, and I actually happen to be speaking to one of the authors this morning. I've been promised a dash 12 any day now. And that draft will, the most recent few drafts, the ones since the working group last call, we have gone in and we have basically agreed to focus this solution on the server client mode for NTP only. And this is a change. It means that we're not solving all of the modes of service for NTP, but we figure for the people that are operating NTP that care about security, this would be a good first step. And I'll get to this a little bit later on, but I think one of the cycles that protocol development gets stuck in is at some point you just need to get something done. You need to get something out there and get it implemented and get experience with it, or you're going to be stuck in forever in this isn't quite right loop. You do run the risk of it being fatally flawed, but it wouldn't be the first thing out there to be fatally flawed. So anyway, so what does NTS provide? Integrity for NTP packets, unlinkability provided you're using the data minimization draft I've already talked about, a request response consistency, which is to avoid replay attacks, authentication of servers, authorization of clients, and support for the client-server mode only. And basically, as I said, the symmetric and the broadcast modes have been deferred. Caveat emptor? Emptor. I forgot how. Oh, caveat emptor. This has not been published yet. And last year I was talking to some people about this, and I was convinced that we would be done by this time this year, and we would be talking about implementation experience. But that is not quite the case. So basically, NTS is TLS for NTP security. What it does is it uses TLS to do the key exchange, and then it uses NTP Extension Fields to secure the packets with the key that has been exchanged in the TLS handshake. And I'm not going to go into this sort of detail, but these are the extension fields that have currently been defined, and they're one of the proposal for the symmetric modes and the others was a use of DTLS, and so they were looking at TLS for the server client modes and DTLS for the other modes. The key here is the security community really doesn't want us to go and invent our own security mechanisms, for good reason. I think they've watched a lot of people over the years get it wrong. So here we are. That's where we are with that. And I'm going to go quickly through IEEE and PTP because this one hasn't really changed as much. Oh, one other thing before I move on from NTP. We do have, for the current draft of NTS, we have a couple of proof of concept implementations. we don't have an implementation that's running in a deployed code base yet. We did a hackathon in March at the IETF, and we're planning another hackathon at the July IETF meeting, and I'm really hoping that we're going to get a production code base with an implementation in there. It doesn't have to be an implementation, it doesn't have to be a production quality implementation, but I want a code base that is operational somewhere to have this added into it. And then we can do interoperability testing. We did do preliminary interoperability testing between the two implementations that we had in March. Those two, we were able to find some bugs. We updated the spec. That's some of the changes that you'll see in the version 12, which is coming out any day now. And the I've completely lost what I was going to say. Oh, so there were some interoperability changes, and we were able to establish interoperability between those two implementations. I'm eager for anybody who is interested, who's a student that might want to try this out. We have lots of implementation opportunities here. So IEEE and PTP. So PTP is probably not as big an interest to this community as NTP, but it is the other major time synchronization protocol out there. It does a lot more in telecom networks, in like factory automation type of networks, and also very precision-oriented ones. If you're interested in this, if you were to look up like White Rabbit, for example, White Rabbit is what CERN is using to synchronize some of their components. So in 1588, we defined a multi-pronged approach, where prong A is to build security mechanisms that would work with PTP. Prong B is to define external security mechanisms that might be in place that we could use. Prong C is to look at architectural mechanisms to improve the security of the system, and that was primarily redundancy. And prong D is for monitoring and management and how you can use that to improve the security of your system. Getting back to the whole point that it's not just about the security protocol that's built into the time synchronization protocol, it's really about the whole architecture and the infrastructure that's around that. So I'm not going to go into a lot of detail on PTP because I do want to leave a few minutes for questions. The point I'm getting to now is the prong A piece, which is if you're going to add security to a PTP packet, this is how you do it. So this is the modification to the PTP packet to support security. What you'll see here is some authentication TLVs, one that's called delayed processing and one that's called immediate processing. And then we have 1588 has the concept of TLVs, and there is a security TLV or a set of security TLVs that have been defined for use with 1588. And so this is the framework of the TLV. I know you are all going to study this quite deeply. This is the PTP packet processing. And basically this says, does it or does it not have a security TLV, and what do you do with it? And then this is a security process. Of course, it's longer and more detailed than the previous one. If you've ever been involved in the IEEE standards processes and the IETF standards processes, they're completely different. And then there's key management. Well, so what we have, key management is always the tough problem. So we have static key management for, static key management will make what currently is existing in the specification work, but of course, again, it's not scalable. And then we have what we're calling instant key sharing and delayed key sharing for GDOI and for Tesla. And this is basically the difference between, are you willing to trust the time information initially before you verify the security, or are you going to wait until you have until you verified the security before you use the time information? Different environments will choose different models. One of the key differences between PTP and NTP is PTP has polling intervals that are much, much faster generally than NTP. So NTP has come from the perspective of a global internet, so it's doing things to reduce the polling interval, whereas PTP goes the opposite direction, and it's like we, send as many packets as possible. If you look at the IEEE 802.1 AS specification, which is a profile, essentially a profile of IEEE 1588, the polling intervals are much, much higher than you would see in NTP. So in any event, there's these two key sharing mechanisms, and so the only thing that's actually normative in 1588 is the specification of the TLV and how it's processed, and all of the rest of it is left to the informative, which is sort of the IEEE way of saying we're going to deal with that hard problem a little bit later on. To really have an implementable solution with GDOI and Tesla is going to require some additional work, and some of this is going to need to be done in the IETF. So there's instant key sharing, and there's delayed key sharing. The external transport mechanisms are MACsec and IPsec. Architecture guidance, monitoring and management best practices I've already talked about. How am I doing on time? Pretty close. So final remarks. I really believe the time is now. And I say this because I think that we've been, in the last week and a half, I've got an email from somebody who I knew is working in this area who was like, we're really interested in this. We're ready to jump on board now, but we think what you've got is wrong, and we have some proposals on how to change it. I have additional conversations with some other folks that have been involved in the effort, and they're like, well, we really think that this is the wrong thing, and we're going to redo the whole thing from scratch. And a proposal is coming any day now. I think at some point you got to move forward, and I think now is the time to move forward. So any implementers, testers, and researchers are welcome, especially somebody who is an outside perspective that can help encourage the now. A little bit now is better than the perfect solution later. And my motto for this whole activity at the moment is done is better than perfect. Contact me if you're interested in helping. I'd love to have some things help. Acknowledgement and thanks, I'm not going to go through these, but the paper that I uploaded when I put in this submission was co-authored by Stefan Fries and Dieter Siebold. Stefan has been the primary driver of the GDOI solution, and Dieter has been the primary driver of the Tesla solution. They aren't the reason why we have two solutions in 1588. They're the ones who helped specify both solutions when the group couldn't decide which one was the one they wanted to go with. And so finally, any questions? All right, if you all don't have any questions, feel free to contact me at any point. My slides will eventually be online. I'm very sorry they aren't there yet, but they will be soon. Thanks.